Hi, my name is Arata Jingu. I'd like to talk about our work LipIO. This work was done in collaboration with my colleague Yudai Tanaka and my intensive advisor Pedro Lopes at the University of Chicago. Here, I am wearing a LipIO device directly on top of my lips. What makes LipIO different from all interfaces is it utilizes the lips as both an input and output surface. For input, the user touches the upper lip with their tongue or the lower lip. For output, the user feels the state of a user interface via electrotactile stimulation, which means the user feels an electrical touch on the lips. Moreover, when the user touches their lips to input, they feel co-located tactile feedback as the touched point. This is key to enabling eyes and hands-free interactions. Now, why did we explore an I/O interface using solely the lips? Well, this is because our eyes, ears, and hands as primary way we interact with the environment. As such, it is very common for users that these busy parts are already occupied with everyday tasks and not available to interact with computer interfaces. Therefore, a lot of effort has been devoted to exploring alternative I/O methods, especially using gestures to control and get feedback from an interface without looking, or moving one's muscles and having the device actuate one's muscles to communicate with an interface without looking. As you can see, the answer is often to leverage the user's hands to do gestures. So the extreme challenge is to explore interfaces that allow for eyes-free, ears-free, and even hands-free, freeing up the hands from being occupied with primary tasks. We propose using the lips as an available alternative modality when hands or eyes are occupied. LipIO utilizes two anatomical principles, the lips' high tactile sensitivity and the tongue's high dexterity. To realize input, it uses a capacitive sensing array with 5 points that you can touch. To realize output, it uses 5 electrodes at the exact same locations as the sensing array, but that touches the user's lip. Once LipIO stimulates these with small electrical impulses, the user feels an electrical touch on one of these locations. Using this, LipIO can be used for extreme applications where eyes, ears, and even hands are not available. Let me show you one such extreme example. This is me biking yet being still able to use a GPS and adjust gears using LipIO. Let me show you how to do it. Now the selected UI page is in the GPS, informing the user to keep moving forward by stimulating the center of the 3 navigation electrodes. Then the user switches to the gear page by touching and flipping the toggle. They feel that the gear is in the lowest setting. The user adjusts the gear by sliding the tank to the highest setting. Finally, they switch to the GPS page again and feel the GPS indicating a left turn. Now, how do we make LipIO work? First, let me tell you how LipIO is engineered. LipIO is comprised of 2 overlapping flexible electrode arrays. An outward-facing array detects capacitive tongue touch, and a lip-facing array provides electrotactile stimulation to lips. The device is flexible enough to fit the curve of the user's lip. We provide all the firmware and schematics from this link. You already saw the device layout, but how did we determine where to place it and how many electrodes to use? We determined the device layout through 3 user studies. The first study assessed which lip was easier to touch with the tongue. Participants were asked to touch tape on both lips and choose which lip was easier to touch. We found that the upper lip was easier to touch in 90% of the trials. This result motivated us to study LipIO on the upper lip. Now we know that we should place it on the upper lip, but how many electrodes shall we use for input? Since There is no prior work for tank-to-lip touch device. A second study first aimed to understand how the user touches the lips with the tank. In each trial, participants felt tactile stimulation in one of the 9 locations and were asked to touch the point they felt stimulation with the tank. Note that this is more complex than finger touches because users are targeting the point without looking, using only the tank proprioception. For example, this user touched the area around 0.7 instead of 6, so they were off by 1 electrode to the target. As you can see, it's not easy to determine the touch point as the tank touches multiple electrodes like the pot finger problem that is so common on touchscreens. Then, we decided to record all 9 capacitive values and test which estimator we should use. Here's 2 simple estimators we use. The centroid estimator outputs the centroid of all the sensor values as the touch point. In contrast, the maximum estimator outputs the highest value sensor as the touch point. We found that the centroid estimator performed better than the maximum one. This graph means the stimulating electrode and the actual touch point were off by about 1 electrode. Our second study was meaningful in understanding our tank touch, but the accuracy of touching the stimulated position was around 41%, not enough as a user interface. To improve this, we considered 2 strategies: decreasing electrodes from 9 to 5 and adding the co-located feedback based on the centroid estimator. With these strategies, we repeated the same procedure as study 2. The result shows the final accuracy reached around 93% without no prior training, and each strategy made a strong contribution to the improvement. We concluded that it was enough for prospective users to play our applications with more training. Now putting these together, let me demonstrate how LipIO enables eyes and hands-free I/O interactions in everyday contexts. First, LipIO creates UI metaphors on the lips. This user is cleaning while their hands, ears, and eyes are occupied. When the visitor comes, LipIO renders the doorbell ringing via its tactile feedback. The user stops the ringing and unlocks the door by swiping the tank on the lips. LipIO renders the door state, and the user feels the door opening and closing. Finally, the user locks the door by swiping in the opposite direction. LipIO also enables a guitar player to use an on-demand guitar tuner while freely moving on stage and keeping eye contact with the audience. Here, the user invokes the tuner by lip smacking. With the LipIO tuner, the user feels how much the string's note is off from the expected note via tactile output on the lips. After completing the tuning, the player dismisses all the tuner by lip smacking again. Lastly, LipIO renders a gaming experience on the lips. Here, the user plays a whack-a-mole game while their eyes and hands are busy. The user starts the game using the lip smack gesture. The mole moves between electrodes randomly. If the user can whack the mole with their tank before it moves, they receive tactile feedback, indicating success. If the user taps an empty hole, nothing happens. Once the user is satisfied with the game, they can dismiss it by repeating the lip smack gesture. In conclusion, we explored leveraging lips as both an input and output interface. Lips have high potential as an I/O interface, and here's some more possibilities for LipIO, such as wheelchair control or braille display on lips, tactile feedback in VL, or as a supplementary modality to other interactions. This is possible because lips are dexterous, sensitive to touch, electrical stimulatable, but also sensitive to acoustic stimulation as I did in my previous WIS work. As the fingers have become a useful modality for today's interactions, I hope that we might witness how Lopes evolved in the following decades as an alternative I/O modality.